Hopefully you all have your green sheets in front of you. I don't, so I'm just going to write up here, and I don't remember what order I wrote it with you folks, but I know that force times change in time is change in momentum is mass times change in velocity. Although that third one I think of as mv final minus mv initial. And I'm just going to kind of mix and match, Hannah, and see just what I can do with this. What can we solve? And again, there's always longer ways to get there, but let's see if we can get there using the impulse combination shortcut equation. Example 1 says this: a force of 8 newtons acts on an object for 10 seconds. I see a force, I see a time. I'm already looking at that. The mass of the object is 4 kilograms. Okay, cool. Maxine, what does A want me to find? What's another? Well, okay, so change in momentum is that. How am I going to find it? Yeah, I think I see a force. I think I see a time. I'm going to use force times change in time. It's going to be 8 times 10. Maxine, I'll bet you can even do that in your head. 80 what? Units. That would be a force. Is this a force if it was newtons? It's not newtons per second. It's Newton seconds. Force times time. By the way, this is the same as, it turns out, kilogram meters per second. Those are interchangeable. If you muck around with the units, Kayla, you'll find you can turn a Newton second into a kilogram meter per second. It works. I don't care which of those you use for impulse. If you just decide, because impulse is change in what? If you decide because it's momentum, you're always going to use kilogram meters per second, and you just decide that, Dean, I'm good with that. I'll usually use as my units what I used to solve it. So Paige, the fact that I use a force at a time, my brain would just naturally write newtons per second. Sorry, Newton seconds. I did it again. Newton seconds, not newtons per second. Newton seconds. If I had done it by multiplying a mass times a velocity, my brain would probably just think, oh, kilogram meters per second. I don't care which one of the two you use. They're interchangeable for momentum, as far as I'm concerned. Cool. Hannah, what's B want me to find? Oh, okay, that not the magnitude of the object. Magnitude of the object's what? Want me to find the impulse. What is it? Too slow. What is it? It's 80. Because isn't impulse the same thing as change in momentum? And that's all I wanted with part B. All I'm asking is, have you figured out that impulse and change momentum, those are the same thing? So it's impulse is 80. And you can write Newton seconds, or you can write kilogram meters per second. I don't care. Ooh, cool. Alex, what's C wanting me to find? I think I'm going to write these two. Impulse also equals m delta v. By the way, what's another way to say delta v? Change in what? Velocity. That's what they want me to find. I've never done this before, but okay. Alex, how would I get the delta V by itself? How will I move the M over? Yeah. Apparently, change in velocity is impulse divided by mass. Okay. What was the impulse? What was the mass? Question told you, got to go read. And I'll bet you might even be able to do this in your head. What's the change in velocity? And I guess since it's change in velocity, what would the units be? Meters per second. Yeah. So what does that mean? Alex, what's the change in velocity? Okay, here's what it means. If your final velocity was 22, your initial was 2. That's a change in of 20. Or if your final velocity was 30, your initial was 10. Ooh, What if your final velocity was positive 5? What was your initial? If your final velocity is positive 5 and your change in velocity is positive 20, what was your initial? Sorry? Positive 25? Let's see. If your final was 5 and your initial was 25, that would be a change in velocity of negative 20. 5 minus final minus initial. Can you see it? It's negative 15. Think about it. Right? If my final is 5 and my change in is positive 20, how can I have a change in velocity of positive 20? I must have started out at negative 15. Add positive 20 to that, and you get 5. Okay? And now you're starting to see why I'm being so fussy about vector notation and direction again. We've really got to pay attention to direction. Oh, in fact, if the final velocity was 12 meters per second north, what was its initial velocity? I think 8 south. Let's prove it. Ready? What's change in anything? So change in velocity is v final minus v initial. You okay with that? Quinn, what are they asking me to find in part D? Read carefully. Initial velocity. I want to get the VI by itself. What's right in front of the VI that I don't like? Swappy dance. I'm not used to having it look like it, but I think what I'm going to do is I'm going to plus the VI to this side, and I'm going to minus the delta V to that side. If I do that, I'm going to get VI equals VF take away delta V. Quinn, what's V final according to this question? Now, although Quinn didn't realize it, he made a proclamation. He said 12. What he really said is positive 12, and positive means north. That in your 12 answer, those are the decisions you just committed us to. 12, because that means it's positive. We don't say the positive, but because it said 12 north, you've decided which way is positive? North. Okay, and I'm fine with that. So, positive 12, take away, what was, Alex, our change in velocity? And I get negative 8. In terms of direct, which way did you say was positive? What direction? So what's this? V initial is 8 meters per second south. And if I was just trying to do this in my head, I just use negatives and positives rather than north and south. One would be positive, one would be negative. Is that a change in velocity of positive 20? Yep. Here's what that means. That means this particular situation, the object was going south. The force was applied to the north that slowed the object down, brought it to a stop, turned it around, and got it going north at 12 meters per second. And how long did that take? Apparently 10 seconds to do that. There's a lot of information packed in there. Example 2. A snow scooter has a mass of 350 kilograms. A constant force acts on it for 60 seconds. The snow scooter's initial velocity is 2.5 meters per second, and its final velocity is 18 meters per second. Okay. Raphael, what's A asking me to find? What change in? What's another word for change in momentum? Starts with letter I. There's impulse. Change in momentum, same thing. So I'm going to write that to start out because it wants me to find that, and I feel better. I've written something down. It's no longer blank. Yay. Which of these am I going to use? Did they give me, Raphael, a force and a time? I see a time. Do you see a force in newtons anywhere? Not going to use that one. You know what they gave me? And? I'm going to use final minus initial. What was the mass, Raphael? 350. Good. VF. Okay. Minus 350 VI. Before we say 2.5, let's read carefully. Is there any hint that there's a direction change, that I need to make this 2.5 negative or anything like that? Do you see anything like that hinted here at all? I don't, but I checked. So VI is just, yep. What's the change in momentum? It's a good question. 350 minus 8 is minus Mr. Dewick times 18 minus 350 times 2.5. You get 5,425. Units. Mass, kilograms, times velocity, meters per second. Oh, we got a latecomer. Got to pause my video and get interrupted. B. Dean, what's B want me to find? Keep reading. By the way, the word magnitude just means how big. So when you say, what's it asking me to find? How big what is, please?
Of the forces.
Yes. Why am I always saying magnitude? Because technically impulse is a vector and it has magnitude and direction, and I haven't given you any direction in this particular question, so I'm being nitpicky and careful. So what does it want me to find?
Magnitude.
Force. I could probably, again, go, don't write this down, F equals what? MA. And I because they gave me mass, I'm sure there's enough information there that I could find the acceleration, and if you do it that way, I will give you full credit. But, Dean, what did we just find in part A?
The impulse.
Is there a version of impulse that has force in it?
FT.
F delta T or just FT? Get the F by itself. And this is why I said to you yesterday, Maxine, the impulse equation is really more of a shortcut. It does explain other stuff as well, but one of its uses is it saves us some time, because instead of having to bother to find the acceleration, Wolf, Dean, what's my... Sorry?
Impulse divided.
Yeah. It's going to be 5,425 divided by how many seconds? 60. So I can turn a 3 line into a 1 line, really. Answer button divided by 60. And I get 90.41. I'll call it 90.4. Units, Dean? Yep. Newtons. Before we move on, I would have no problem just asking you part B without asking you part A first. And again, some of you would say, oh, F equals MA, I'll find A the long way. Some of you would say, well, I can find impulse and then do that. Example 3, a rocket of mass, blah, 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 starting from rest. You know what? I would probably mentally underline the phrase from rest, because that tells me something. Is acted upon by a net force of blah, blah, for blah, blah. Ooh. Paige, what's this want me to find? Okay. What did they give me? A mass? Yes. A VI? Yes. A force? Yes. And a time. I could do this the long way, but again, here's what I'm going to try doing. I'm going to try being clever. I'm going to say impulse equals impulse. But here's what I'm going to write. Watch. I'm going to say force times time equals m v final minus m v initial. Impulse equals impulse. Yes? Paige, do I know F?
Yes.
Do I know T?
Yes.
Do I know M? Did they tell me the mass? Yep. VF is what they want me to find. I know M. Do I know VI? Oh, you know what? From rest. Get the VF by itself. What's the M doing to the VF? So? You understand, what this would have been probably a 4 or 5 step question if I did this all in chunks, but the fact that I can come up with an equation that combines force and time and VF and VI, it's a big time saver. In fact, I think I'll get this. VF equals force times time divided by mass. Not on your formula sheet, but yet another equation for VF. I've never bothered writing it down. I can derive it if I need it, but now it's plug and chug. Force, 2.3 times 10 to the 4th. Time, 120. Mass, 2.6 times 10 to the 4th. This is good review of how you enter scientific notation on your calculator, so this would probably be worth trying out. And I get 106? 0.153, 106 if I go to 3 sig figs? Okay. And direction, I guess, well, rocket, what direction? Starts with the letter U. Up. Example, I'm going to pause for a second. Hopefully I haven't really taught you anything new so far. I'm just letting you know, with a bit of cleverness, we can use this impulse equation to save us some time. The idea that change in momentum and force times time and final minus initial, mv final minus mv initial, are the same thing and interchangeable, and we can move them around and mix and match. A car of mass 1,600 kilograms moves at 32 meters per second. Ooh, Eliana, what's example 4 wanted me to find? Okay. Again, don't write this down. I could go F equals ma. And I bet you there's enough there to find A. Or, did they give me a time? Did they give me a VI? Did they give me a VF? Halt. 0. I can use this same impulse equation. I can say force times time equals mv final minus mv initial. Oh, which one of these is 0? And so I think that whole thing vanishes. In fact, what I really get is this. Ft equals negative mv initial. What am I trying to find? So? How? Yep. Apparently yet another equation for force that I'm not going to bother trying to commit to memory. Force equals negative mvi over t. It's going to be negative m, 1,600, vi, 32, all over t. I think I can do this in my head. Sure I can. It's going to be negative 32,000. Double check me. Think so. Yeah. And newtons. What's the negative telling me? If the car is driving north, which way do we need to apply a force to bring it to a stop? South. Or if I just generalize, if the car is driving forward, which way do we need to apply a force to bring it to a stop? Back. And I'm kind of comforted by the fact that the negative did show up. That probably suggests I've set this up right, because that's kind of a Captain Obvious. Yes, the force has to be in the opposite direction of the motion. The negative is telling me that. Yay, I probably did this right. Example 5. A rock falls from the top of a 40-meter high building and strikes the ground below. What is the force, magnitude, and direction this time? Of the ground acting on the rock if it comes to a stop in 0.350 seconds. Okay. Nicole, what's this asking me to find? I might be able to do this with F equals ma, but did they give me a time? I think I'm going to try doing this with impulse. I think I'm going to try going, again, force times time equals m v final minus m v initial. I did notice comes to a stop. What's V final in this case? Mr. Dewick, I thought V final when you hit the ground wasn't 0. This is after we've hit the ground. We're asking what's the force that the ground applied? What's V initial? That's how hard we hit the ground at. First of all, how would I get the force by itself? Folks, do you mind if we go? In fact, we're going to get this. Force equals negative mvi over t. Okay. Do I know m? Yep. Do I know t? Do I know vi? What? mg? First of all, mg, that would be mass times gravity. That would be weight. What's weight measured in? Is newtons the same? No. Mass is measured in kilograms. Weight is measured in newtons. Is newtons the same as velocity? I'm going to say that's a Verizon guess. We don't know VI. We don't know how hard it hit the ground at. Now that VI is how hard it hit the ground. That's how fast it was traveling when the ground began to bring it to a stop. But that's also how hard it hit the ground at. You know what? Let's do a little free fall over here. Okay. What do we want to find? Well, in free fall, what's VI here? It's 0. What do I want to find in this free fall question? Not VI, but I want to find VF, and then I'll take that VF. That's going to be VI when the ground begins to bring it to a stop. We've seen this happen a few times before, where a final became an initial in the next step, or an initial became a final. We've seen this little step before. What else do we know? What's D? Don't say 40. Don't say 40. Cliff. What else do we know? Is that time how long it fell for? Or is that time how long it took the ground to bring it to a stop? Okay. So do I know time in free fall? No. You're missing something really obvious. Yes? More specific? More specific? Right? My goodness, Mr. Dewick, my phone made a noise. I can't believe that happened. I owe the class Timbits. I didn't put it on vibrate this morning, and it's supposed to be on Do Not Disturb, but Apple changed their Do Not Disturb settings in iOS 15, and I haven't figured them out yet. Irritating me. I'm embarrassed. Which equation? What's VI? So we don't need to get it, but we'll move it over in a sec. First of all, just write me an equation for VF, getting the VF by itself.
Oh, VF squared equals
Get the VF by itself, not VF squared.
VI. Sorry, VF equals the square root of 2.
Is she right? VI is 0, yes. So gone. Square root, okay. So it's going to be the square root of 2 times negative 9.8 times negative 40. And I get, oh, what do you get? Yeah, why is that wrong? I think this time because it's velocity, we know that we don't want the positive root. Which way is this thing traveling when it hits the ground? Okay. And that's what I'm going to walk over to here. By the way, we've just committed now. Negative means which direction? Negative means which direction? What does positive mean? So in our final answer, we'll have to use that to interpret direction because it did say magnitude and direction for the force. Okay. It's going to be negative, what was M? I've scrolled down, Nicole. What was M? 2.5. VI, negative 28. And 0.35 seconds. Ooh, this might actually work out even, or nice at least. Negative 2.5 times negative 28 divided by 0.35. Ah. Do you get 200 even? Direction. How do I know? Okay, committed to that. By the way, if you hadn't put the negative there, it's not wrong. It just means you've decided that down is positive. You would get a negative answer here. What's negative down? Gotta be up. As long as you're consistent, you're okay. But this is why I keep writing all the, in fact, I should have put a vector sign right there and a vector sign right there and a vector, just to remind myself, pay attention to direction. 200 newtons up. And yeah, of course, the ground applies the force up to bring a falling object to a stop. That makes sense. I like example 6, I like example 6, I like example 6. Example 6 is a nice question. Why would I say that? Oh, okay. A 4.2 kilogram ball moving at 4.65 meters per second east hits a wall. I've hit the wall all morning, Mr. Dewick. Shut up. The wall exerts a force on the ball of 350 newtons to the west for 0.0750 seconds. Find the final velocity, magnitude, and direction. I guess it'll either be west or east of the ball. This is a pretty tricky question to do without impulse, although you can all handle it. But I think we're going to use impulse. Now, how did I figure that out so fast? I saw a force and a time. See it? So I'm going to start out going impulse equals impulse. For, you know what, just to mess with you, I'm going to go mv final minus mv initial equals force times time, because you should be comfortable with these things on either side of the equal sign. I don't care which way you write it, but I noticed I've been putting the F on the left every time. Let's put it on the right, just for giggles. Mesa, what are they asking me to find? I'll put a dot above it. I want to get that by itself. How? Well, what's right next to the VF? How will I move that M over eventually? Remember that, remember that, remember that. What else is on the same side? A minus MVI. How will I move that over? Add. Which one am I going to do first? Am I going to divide by M, or am I going to plus the MVI? Reverse bedmass. You're adding and subtracting first. Remember all this? This is part of why I snuck all that in a couple of units ago, is so hopefully you can look at this and you can say, Mesa, what's going to drop down like a domino? The FT, right? Then what? Plus MVI. Then that equals VF. That's a really weird equation for V final. Wolf, am I going to bother trying to memorize that? No. Am I going to want to add that to my green? Well, no, because in a different situation, it could be totally different. I cannot come up with all of these, but I can derive them from the impulse Swiss Army knife equation. Alrighty. Pause. Mesa, can you read to me this word that starts with capital E? Can you read to me this word that starts with a capital W? Before we plan our attack, we need to decide which way we want to be positive and which way we want to be negative. So you're going to decide for us. Mesa, would you like east to be positive or negative? Are you positive? That's funny. Say it again. Okay, everybody, I'm now going to quickly go through the question, and anything that's east, I'll put a little positive in front of it. Anything that's west, I'll put a little... Okay, so you can do this with me. Definitely positive right there. Yes? Ooh, force to the... You know what I need to put in front of this 350? A negative. Yes? And if I didn't do that, if I wasn't paying attention to that direction change, I'm going to end up with the incorrect answer here. But now, why don't I have to put a positive or a negative in front of time? It's a scalar. No direction. Much like your never mind. Scalar. So, okay. Mesa, what's F? No, it can't be 350. That's impossible. What? That's a silly mistake. Don't do that. Time. And then there's a plus sign and an M, 4.2. VI, positive 4.65. All divided by 4.2. I'm going to kind of argue here, Victor. The physics, the math here isn't that tricky. You got to pay attention to directions. It's really easy to make a silly mistake. And all I can say, I haven't come up with a dumb, stupid way to remember stuff here. Just pay attention. Don't. What do you got? I'm hearing a negative 1.6. Anybody else? Even? Yeah. Negative 1.6. Anybody? Yeah. How would you report that as magnitude and direction? 1.6 meters per second at... What did Mesa say negative was? West. I guess this ball came in, hit the wall, and bounced off. And oh yeah, west now doesn't surprise me. It bounced off, it changed direction, but we've done a nice proof of it as well. Is that all right? I like example 7. I like example 7. Example 7 is a nice question. A rifle accelerates 12 gram, but nice try, Mr. Dewick. 12 grams, how many kilograms? How do you go from grams to kilograms? What does kilo mean? It's 1,000. So do you go 12 times 1,000 or 12 divided by 1,000? Okay. hopefully you've held enough objects to know that if you go 12 times 1,000, 12 grams is not 12,000 kilograms. 12,000 kilograms, that's the size of several trucks. 12 grams, you can hold that and hardly feel it. So divide by 1,000. So what is that? 0.0 something, 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 something. What is it? Okay. From rest, I would probably notice that. To 250 meters per second, the rifle barrel is about 0.85 meters long. Okay. Kevin, what does A want me to find? Change in momentum. Which version of the many change in momentum equations am I going to use here? I don't have one that says mv. I have one that says m delta v, but I definitely don't have one that says mv. By the way, mv, that's just steady momentum, which is not the same as a change in momentum. So I got to jump on you for that and say, don't say that, don't even think that. M delta v, is that what you meant to say? Then say it. Thank you. Which I'm going to write as mv final minus mv initial, because change in anything is final minus initial. Oh! Kevin, what was the initial velocity here? Yeah, in fact, what's the initial velocity of any bullet? I've never seen any gun that has the bullet take a running start and then fires it, so 0. Okay. Easy peasy. 0.012 times 250. What do you get? Do you get 30? No. 30? Is it 30? 3. I missed a 0. Jeez. 3? Okay. Oh, not newtons. What did we just find? So I can write that as Newton seconds, although since I went mass times velocity, I would probably write it as kilogram meters per second. Someone's phone needs to be put on vibrate. Yeah, right, Mr. Dewick. Yeah, okay, fine. Kevin, what's B want me to find? What did I find in part A? So maybe I could go force equals impulse over time, and I just got the F by itself in my head. I didn't actually write F times T equals impulse. I looked at it and I said divide by T. Is that too fast? Did they give me a time? Or maybe I want to go F equals MA. Did they give me an A? So I'm going to write them both down. Here, it's half of one, or 6 of one, half a dozen of the other, which is an expression that basically means, what do you want to do? Do you want to find time, or do you want to find A? Because apparently we got to find one of them no matter what. So I can either find A and go MA, or I can find time and go 3 divided by time. Pick. No. Read the question and ask yourself, what's going to be easier to find? Is it going to be easier to find time or A? And that's how I would do this. I'm that lazy. I would think to myself, which is going to be less work? Pardon me? I think so, actually, yeah. How can I find A, Kevin? I don't know the force. That's not going to help. You're telling me A equals that over that. I'm trying to find F. Doesn't help me at all. I still agree with you. I think it's easier to find A. How can I find? So we need to make a list. Fine. Kevin, what's from rest? What's 0? Thank you. What's that 250? What's that 0.85? I can find an A or a T from that. What's going to be easier, to find an A from that or a T from that? Yeah. I think I can go, which equation, Kevin? Can you get the A by itself, please? What happened to the VI squared? It's 0. If you wanted to get the time by itself, I think you're using the second equation, the one with the brackets, because that's the one that has the D and the VI and the V. It's doable, but I would use this one. I would find A. Okay? Yeah? Okay. So I would walk over here and I would say, rather than using impulse, this time it's not going to save me any time. Instead, I'm going to go mass VF squared over 2D MA. I could have calculated it, but I was lazy. I just stuck the letters in there. Hey, another equation for force. Don't memorize it. M, 0.012. VF, 250. Don't forget the squared. All over 2 times 0.85. Do you get 441? Or am I wrong? Someone else? Yeah? 441 newtons? Kevin, did it say magnitude and direction? Or just find the force? Although, I guess forward, through the barrel, out the barrel, because that's how bullets work. Is that all right? So don't get locked into the impulse equation. You have learned enough physics so far this year. You've got a lot of tools at your disposal. Example 8. Okay. It says, consider the diagram at the right for the next 3 questions. The diagram depicts initial and final velocities of an 800 kilogram car in 2 different collisions. I guess in case A, the car comes in at 5, bounces off the wall at 4. In case B, the car comes in at 5 and comes to a stop. In which case does the car experience the biggest momentum change? Case A, case B, both the same, or we need more information? You know what? We're going to vote. How high we hold our hand up is how sure we are of the answer. So look at case A, look at case B. In which case does the car experience the biggest change in momentum? Who says, Mr. Dewick, case A? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. He says, no, case B. 1, 2. Who says both the same? You good? Oh, I just distracted you? Sorry. Who says we need more information? Some of you didn't vote. I'll get you next time. Convince me. How do we find impulse? It's on your green sheet. How do I find impulse? It's on your green sheet. How do I find impulse? Yeah. In fact, that's, although it's force times time, I don't think force times time is going to help me analyze this. I would be thinking mass times change in velocity, or mv final minus mv initial. So which car experiences the biggest impulse? Do they have the same mass? Yeah. Do they have the same change in velocity? No. What's the change in velocity in case B? I like that. He said -5. So Quinn has decided that right is positive and left is negative, and he went final minus initial, -5. What's the change in velocity here? It's not 1. It's -9, right? -4 minus 5. Definitely case A has the biggest change in momentum. 2, which car has the biggest impulse? Everybody. Which one? Why? Because impulse and change in momentum are the same. Okay. Oh, what is the impulse of the 800 kilogram car in case A? Well, it would be mass times change in velocity, which is final, -4, minus initial, +5. Oh, it just wants the magnitude, which means we can ignore the negative. So what's worse, a head-on collision where you come to a stop, or a head-on collision where you bounce off the other car and go backwards? Oh, way worse. Way worse. More impulse. Same amount of time, so force must have gotten bigger. Oh, I just did a, sorry, I thought I should have asked that question. I haven't taught this lesson for 2 years, so I just spoiled it. What type of collision is worse for a passenger if we assume the initial velocities and the time of impact are the same? A head-on collision where the two cars stick together, or a head-on collision where the two cars rebound apart? Which one? Why? Bigger delta V. Which means bigger impulse, which means bigger force. Yeah. Example 10. The diagram below depicts the changes in velocity of a ball that undergoes a collision with the wall. Indicate which case, A or B, has the biggest change in velocity. Put it face down in the appropriate block, Camille, when you're done. Thank you. Greatest acceleration. Okay, you know, let's do first of all, which one has the biggest change in velocity? What is the delta V of this one here? Not 5. What is it? Either negative or positive 15, depending on which way you let be positive or which way you let be negative. Definitely has a magnitude of 15. What's the delta V here? Yeah. So which one has the biggest delta V? B. Explanation? Well, we solved it. Which one's going to have the biggest acceleration? If we assume these both occurred over the same amount of time, which one has the biggest acceleration? Well, remember, way back when I defined acceleration as that. So which one has the biggest change in velocity? Which one has the biggest delta V? B. Which one has the biggest acceleration? Which one has the biggest impulse? Are you spotting a trend? B. Which one has the greatest F delta T? Oh, That's also impulse. Okay. Can you see how, though, if you don't pay attention to direction, it's very easy to glance at this and think 5, 2. Not as bad. No. We have to take direction into account now. It's a vector. So especially if you notice there's a rebound, and I will give you a couple of rebounding questions in the future. One would be positive, one would be negative. Doesn't matter which way. What's your homework? You can do number 1, number 2, number 3, number 4, number 5, number 6, number 7, number 8, number 9, number 10, number 11. Those are all really one big question. 12 is good. 13 is good. Uh, 14 is good. You can skip 15. I'm going to skip 16. 17 is good if you water ski. 18 is good. Let me look here. Okay. Kind of scanning through. 19 is good. We did one like 19. 20 is nasty. See if you can figure it out. We'll skip Calvin and Hobbes. I do like 22. I do like 23. That's a lot. And it's a Friday, and I'm not wild about giving homework on a weekend. So probably I'm going to press pause a little bit, or I'll do half a lesson on Monday. You are going to get a take-home quiz on this on Monday on what we've done so far as well. So I'll give you some time to work on that as well. Got a couple of videos to show you, though. Put your pencils down, look up. Crumple zones and momentum? Yeah.
Hello and welcome to today's lecture from Britain University.
Hi, I'm Nick.
And I'm Jane.
Today we're going to look at momentum and how we can use it to understand why we need crumple zones in our cars. Let's start off by looking at some theory on the whiteboard.
So there's a student project. They did a pretty good job, though. It's a good explanation.
Let's remind ourselves that momentum is equal to mass times velocity.
Yes? Okay. Paige, you want to sit up? Thank you, dear.
If our car weighs 1,000 kilograms and it is travelling at 25 meters per second, what is its momentum?
What is its momentum if it's 1,000 kilograms and 25? You can probably do this in your head. What is it? 25,000 kilogram meters per second. Okay.
That's right, you've got it. 25,000 kilograms meters per second. What happens when a car hits a wall? Because the car's velocity becomes zero, its momentum must change to zero during the collision. We can use the change of momentum formula to allow us to find the force that acts on the driver during the collision. Rearranging the formula, we get force is equal to change of momentum divided by the time over which the collision acts.
We did that one several times today.
Now we can use this formula to see how we can reduce the force on the driver. Because the change of momentum will be the same for any specific collision, if we increase the time, it will make the force smaller. Now we can put this theory into practice by looking at crumple zones in a real collision. Let's go over to our brave stunt driver Ollie. Ollie, are you ready to go?
I think so.
So here's a car with a crumple zone. Here's a car without a crumple zone.
Oh dear. I hope Ollie was okay after that second crash. Now let's go back to the whiteboard to see if we can work out the forces involved in those two collisions. So the car had a mass of 500 kilograms and a velocity of 10 meters per second. In the first collision, when the car had a crumple zone, the car and the wall were in contact for 1 second. So if we put those numbers into the formula, we can see we get a force of 5,000 newtons. Now let's look at the second collision. In this one, the car had no crumple zone. So the car had the same change of momentum, because it was still 500 kilograms, going at a velocity of 10 meters per second, but the contact time between the wall and the car was only 0.2 seconds. So if we put these numbers into the formula, this time we get a force much greater of 25,000 newtons, which is why poor Ollie ended up being thrown out of his seat. You'll be pleased to know that Ollie has made a full recovery and will be ready to do some more experiments for us next week. That's all for this edition. So it's goodbye from me.
And goodbye from me.
Good explanation. I got a couple more videos to show you, but I want to give you some time to start the homework, so I went a little longer than I planned. I apologize. I haven't taught this lesson for 2 years.